Hi everyone. So before we go over worksheet number 11, I wanted to discuss a couple of really important concepts. The first of which is what an oxidizing agent is, and then the second is what a reducing agent is. So here I've got a couple different, say, atoms. Say I got an atom here that has some electrons, and here I've got three other atoms that have an electron as well. So for something to be an oxidizing agent, what we're saying is that this is an atom or a molecule that does an oxidation on something that's surrounding it. So here we've got some surrounding atoms. What's going to happen here is if these are electrons, these electrons are going to get taken up by the oxidizing agent. They're going to get taken up like this. All right, so we're going to take up these electrons. And now, let's suppose these are the atoms that had these electrons initially. What's going to happen now is the oxidizing agent now has all of these electrons. So the oxidizing agent has gained electrons. And now all of these atoms that are around the oxidizing agent have lost electrons. Okay, so all I wanted to show here is that the oxidizing agent, which is this right here, gains electrons. And where does it get those electrons? It gets those electrons from nearby atoms. And so it is oxidizing those nearby atoms. And by that, what I mean is that those nearby atoms are losing electrons. All right, so by losing electrons, these are now oxidized. And so the oxidizing agent is what does the oxidation on nearby atoms. So nearby atoms lose electrons, and the oxidizing agent gains the electrons. All right, so let's go over to the reducing agent. And let's go ahead and set up, construct a similar situation. So I've got a few different atoms here. Okay, let's suppose that these are some surrounding electrons and let's say these are surrounding atoms, and they have electrons here. And this is an atom that corresponds to the reducing agent. And so here we've got three electrons that are on the reducing agent. So by saying that we're reducing something, we're saying we want to reduce the surroundings. So by reducing the surroundings, that means the surroundings are now going to acquire electrons or gain electrons. So these electrons here from the reducing agent are going to reduce the surroundings. Just like this. So what I'm saying here is that now the reducing agent, let's go ahead and draw this out. If you notice here, the reducing agent has now lost electrons. And where did it give the electrons to? Well, it gave the electrons to these surrounding atoms. So the surrounding atoms have gained electrons. So the surrounding atoms have been reduced, and they were reduced by the reducing agent. So it's the reducing agent that does the reduction on the surrounding atoms, and so by doing so, it had to give up electrons, and by giving up electrons, it itself, the reducing agent, is being oxidized. Okay, so just want to recap. Oxidizing agent is what oxidizes surrounding molecules or atoms. Okay, and by doing so, it gains electrons. So it takes those electrons up, it grabs them from whatever's around the oxidizing agent. So thereby oxidizing whatever's surrounding it. And then on the reducing side, the reducing agent is what reduces molecules or atoms that are around the agent. And thereby the agent loses electrons, and it loses them by giving them to the surrounding atoms. So that's how oxidizing agents and reducing agents work. So just simply bouncing off of that, well, I'll go ahead and keep this up. number 1, where it says here A or N blank is a substance in a redox reaction that gains electrons, we just have to think about where the electrons are going. So is it an oxidizing agent, or is it a reducing agent, or is it a reductant? So let me just clarify here that by saying reducing agent, we can also say reductant and mean the same thing. And we'll see the same sort of situation on number 2. So really we're asking, is this an oxidizing agent or a reducing agent? So we're gaining electrons. So the agent here is gaining electrons from its surroundings, which means that the surroundings had to lose those electrons. And that means that the surroundings were oxidized. Okay, so we are oxidizing the surroundings, therefore number 1 is an oxidizing agent. It's the oxidizing agent that gains the electrons, and it gains them by oxidizing its surroundings. Okay, so number one then is A, oxidizing agent. Now for number 2, we're just asking the same thing, but for the other scenario. A or N blank is a substance in a redox reaction that loses electrons. So here we're losing electrons. Where are we losing them to? Where are we giving them up to? We're giving them up to the surrounding atoms or molecules. And so those surrounding atoms or molecules are now gaining electrons. Therefore, they are being reduced. And so the thing that does the reduction is the reducing agent. And it is what is losing the electrons. It's giving them up to its surroundings. Therefore, the thing that loses electrons is the reducing agent. So then number 2 is B, reducing agent. So I would just take some time and familiarize myself with what's actually going on here in the terminology. I do want to point out that by saying oxidant or oxidizing agent, we mean the same thing. So it's just like saying reductant and reducing agent means the same thing. Oxidant and oxidizing agent mean the same thing as well. They're synonymous terms. So keep in mind that the oxidizing agent is getting reduced and the reducing agent is getting oxidized. Okay, and if you just picture something like this and follow where the electrons are going, then it will be clear as to whether something is an oxidizing agent or a reducing agent. And you will then just intuitively be able to see, is the agent gaining or losing electrons? And from there you can determine whether it is being reduced or oxidized itself. Okay, so take some time. I know this is really confusing. I have to stop and think about it too, but it'll be worth your time to figure it out and become familiar with how this terminology works, because then when you see this on the exam, you're going to be comfortable with it, and it will be no big deal. Okay, so A is for number 1 and B is the solution for number 2. So now for number 3, we're being asked to determine what the oxidation number on the sulfur here is in the polyatomic anion sulfate, SO4 2-. So this one is really quite simple as long as you remember that each oxygen is going to carry a -2 charge with it. Okay, so let's go ahead and say that let's first of all say that the oxidation number for sulfur, I'll just label it like this, plus 4 times, because we've got 4 oxygens here, of the oxidation number of oxygen, all together has to equal the charge of the molecule. And the charge of the molecule is -2. Okay, so here's how we would do this. We know that the oxidation number on each oxygen is -2, so let's just go ahead and plug in the oxidation number for oxygen is -2. So we still don't know what sulfur is, so we'll just leave it like that. Plus 4 times -2 equals -2. Alright, so this is just -8. And now let's go ahead and add the -8 over to here. So we'll take Take this and add it to both sides of the equation. And now the oxidation number on the sulfur becomes -2 plus 8, which equals +6. Oh, there we go. So you can see. So the sulfur needs to have an oxidation number of +6, so that 4 oxygens, with each with a -2 oxidation number, can combine and give you a molecule whose overall charge is -2. Okay, and so we see that here. So now if we plug 6 back into, let's do it here, 6 back into here, so we got 6 plus 4 times -8 is 6 minus 8, and that does indeed give you -2. So it works out with the charge of the molecule, so the oxidation number on the sulfur is +6. So that would correspond to C as being the correct answer for number 3. So number 4 now piggybacks off of number 3, because what we can do is we can learn we can use what we learned from number 3 to figure out what the oxidation number is on the iron. So we know from number 3 that the oxidation number, the numbers of the sulfur and the oxygen, provide that the charge of the sulfate is a -2. Okay, so we also know that the charge of the overall molecule here, the iron with the sulfates, is neutral. So it's going to be 0, right? So the oxidation number of the iron times 2, because we got 2 of them, plus 3 of the sulfates, so we got 3 times the oxidation numbers of the sulfates, is going to give us a total charge of 0. And the reason it's 0 is because the molecule is overall neutral. Well, okay, we just stated here that the sulfate oxidation number is -2, so let's go ahead and plug that in, -2. So now we just have 2 times the oxidation number of the iron, plus 3 times -2 is just -6, equals 0. And now we can just move this over and say that 2 times the oxidation number of iron equals, moving this over, equals +6. And then just dividing both sides by 2 tells us that the oxidation number on each iron then is 3. So looking back on number 4, that means that number 4 here is B, so B is the correct answer for number 4. B is 3, so the oxidation number on each iron is 3. And so we can +3, let me be specific there, it's +3. So we can just double check and make sure. So if we have 2 +3 charges, then the total positive charges is 6. And then here, if we have 3 -2 charges, that gives us a total of 6 negative charges. So +6 plus -6 gives us 0, and the molecule is indeed neutral. So that works out with the molecule, and all of the charges balance out, and that works with our stoichiometry here of having 2 irons and 3 sulfates. So it works, and I think that's a perfectly reasonable answer. If you're ever unsure, you can just always, just like that, go back and look at the molecule and see if it works out. If you get something here that does not end up balancing out to the charge of the molecule, then you should probably go revisit your work. But if you get something like this, where you get 6 positives and 6 negatives that add together to give you a neutral molecule, so 6 plus -6 equals 0, then you know that you got the right oxidation number. Okay, so 3 here is the oxidation number for the iron, which corresponds to B, so B is the correct answer for number 4. So now for number 5, we're being asked to predict which of the 4 elements listed in the choices is the strongest oxidizing agent. So we have copper, nickel, zinc, and sodium to choose from. And here I have provided for you the activity series. So all the activity series is telling you is just how strongly reducing is a particular element. And of course, this isn't exhaustive. These values here that determine the listing are numbers that are experimentally determined, and this is done for all kinds of molecules, all kinds of elements. This is just a small selection out of them that gives you information pertinent to the material from the worksheet and the quiz. So just keep in mind that you might see something on here that, or you might not see something on here that you might think is missing. Don't worry. There's some other table that has it. Most likely a reduction potential has been measured for it. So, but this is a small piece of that shows you sort of like a general trend where you have enough here to see that that you have a distribution of elements all across this table, all up and down this table, that go from being weakly reducing to strongly reducing elements. So what do we mean by strongly reducing? Well, if we thought for a second about the example that I discussed earlier, where we talked about what a reducing agent is, then we can relate that to this. Let's take a look at lithium here. Lithium really wants to give up its electron. So it's shown here as giving up its electron and becoming lithium plus, and giving up an electron. So by doing so, what it's doing is it's giving up that electron to something that's around it that can accept that electron. Okay, so by having something around it that can accept that electron, what's happening is it is reducing its surroundings. And lithium happens to be the element that does it the best. So it has the most reducing power, which means that it will reduce just about anything. So it has this I guess it would be the strongest reducing agent, which is why it's on the top of this table. And things that are listed down below lithium are elements that are also fairly strongly reducing, like potassium, barium, calcium, and sodium are fairly strongly reducing, but not quite as much as the lithium. So lithium will reduce just about anything, but the potassium, barium, calcium, and sodium are not as strong of a reducing agent. And so there are some things that they just can't reduce. And then as we work our way farther down on the table, we start to get to these weakly reducing atoms. And so these atoms are actually atoms that really honestly suck at reducing things. So they would serve as excellent oxidizing agents, meaning that they will happily take up an electron and so take that electron away from their surroundings, thereby oxidizing their surroundings. So when you see something like this and you see it only showing strongly reducing or weakly reducing, keep in mind that a strongly reducing atom is something that is a very bad oxidizing agent. Okay, but as you work your way down the table towards the more weakly reducing atoms, as they become increasingly weakly reducing, they become increasingly stronger oxidizing agents. So they become better and better at oxidizing their surroundings. Okay, so that's how you can read this table. So now, according to the activity series, which of the following would you predict to be the strongest oxidizing agent? So for number 5, let's look at sodium. So sodium's up here. And let's see if we can find something that's a little bit lower than sodium, because sodium is still a pretty good reducing agent. It kind of wants to give up that electron, so we're not gonna think that's a very good oxidizing agent. Let's try to move down the table, see if we can find something lower that's a better oxidizing agent, so a poorer reducing agent, you could say. And here's nickel. Okay, so nickel is going to be a better oxidizing agent because it will more readily take up electrons from its surroundings and oxidize them. And let's see if zinc is any lower. Oh no, zinc is up here, so that's certainly not going to be it. And let's try copper. Okay, copper is all the way down here. So copper, being the lowest on the table, tells us that it's the most weakly reducing element. And so by it being the most weakly reducing, that means that it's the most readily oxidizing element. So it's going to oxidize its surroundings. And so that's going to be the strongest oxidizing agent. So copper here then is the right answer for number 5, and that would be A. Now, moving on to number 6, according to the activity series, which of the following would you predict to be the strongest reducing agent? And the strongest reducing agent is simply the one that's on the top of the table. It's the one that's going to reduce its surroundings the best. And that's the element that gives up its electron the most readily. And that can be shown, can be seen here as lithium. So lithium is the element that most readily gives up its electron. And so therefore it is the strongest reducing agent. So D is the correct answer for number 6. Okay, for number 7, we're being given this very exciting reaction of chlorine gas and sodium metal combining to make sodium chloride. And by exciting, I mean this is a really cool reaction. You can look it up on YouTube, and it's just really interesting to watch this gaseous chlorine gas reacting with the sodium metal to make salt. It's really quite remarkable. So here we have obviously a redox reaction because we're being asked about what element is reduced and which is being oxidized. So let's go ahead and try and figure this out. Anytime you have an element, or an atom, I should say, that is in its elemental form, its oxidation number is going to be 0. So chlorine here is just in its Cl2 state. So it being in Cl2, its oxidation number is 0. So each chlorine atom is going to have an oxidation number of 0. It's in its elemental form essentially, and sodium here is also in its elemental form. So sodium, the sodium metal, is going to have an oxidation number of 0. Okay, that is really crucial. Now we can move on to the sodium chloride, and we see that the well, of course this isn't necessarily balanced. Actually, you could put a 2 right here and a 2 right there in order to make that balanced, but that's not really crucial. We're looking at oxidation numbers here, not really mole or mass quantities. So I do recognize that's not balanced for mass or moles, but it doesn't really matter. Here what we're seeing is that the sodium and the chlorine have now undergone a redox reaction. That's really the important thing. So the sodium here goes from being elemental at a 0 charge to being ionic. Right? Sodium chloride is an ionic molecule. So the sodium will have lost an electron, right? Because it becomes sodium plus. And the chlorine here goes from chlorine 0 to chloride, and it took up that electron from the sodium, and therefore it becomes Cl minus. Okay. So this is really quite straightforward. The sodium has a plus charge, and the chloride now has a minus charge. And that's how you make sodium chloride. So, which element has been reduced? Well, the element that was reduced, so I can write this out, reduced means gained electrons, right? So by having gained electrons, what we've done is we have reduced our negative charge, essentially, right? So we've reduced our charge, and it's become more negative because we've added electrons to the atom, and since electrons carry negative charge, the charge on that atom is going to become more negative. That's kind of how I think of it. It drops the charge, you could say, and so the element is being reduced. It's gaining electrons. So which one is it? Well, it's the one that becomes more negative. It obtains a more negative oxidation number, and that would be the chlorine. So chlorine goes from 0 to -1, so it gained an electron, which means that it's the chlorine that gets reduced. And then conversely, we got the sodium here, so oxidation means a loss of electrons, right? So the sodium here is the element that gets oxidized. It gave up its electron to the chlorine. So by having given up its electron, it has been oxidized. It lost that electron. So the correct answer is A. So A tells us that the chlorine has been reduced and the sodium has been oxidized. So together, A is the correct answer for number 7. Number 8 asks us to revisit the activity series and determine what the outcome would be of a reaction between sodium metal and copper ion. So let's think about this for a second. The sodium, being a metal, has a charge of 0, an oxidation number of 0. The copper, plus, being aqueous, has a charge of +1. So what we're saying here is we want to ask the sodium to give up its electron to the copper, and then at the same time we're going to ask copper to take that electron up. So what we can do is we can look at the activity series and see if this is a process that can happen, and essentially that will tell us if there's going to be a reaction or not. So here, let's find the sodium. So here's my sodium. And let's find the copper. Okay, there's my copper. And what we want to do is we want to first of all say, is sodium going to readily give up its electron? Yes, absolutely. It will readily give up its electron because it's a strong reducing agent. It's very good at reducing. It's one of these elements that rapidly releases an electron. Now, copper over here is one of the elements that is a weak reducing agent, but remember what we said, a weakly reducing agent is a good oxidizing agent, which means it readily accepts electrons. So it readily gets reduced itself. So if we have a species here that is willing to give up electrons to be oxidized to serve as the reducing agent, and we have something here that is readily reduced, something that'll take up those electrons, then we have a redox reaction that can be favorable and can happen. So D, being no reaction, is not the correct answer, because we see here that if we start with an electron up here from the sodium, sodium will readily give it away and copper will fairly readily take it up. So we know that it's not going to be a no reaction. Now we just have to figure out where the charges are going to be and what those charges are, because that's what's going to distinguish between A, B, and C. So the sodium here starts out as a neutral sodium, sodium 0. When it gives up its electron, it becomes sodium plus, just like in the sodium chloride. Okay, so that instantly eliminates A because sodium does not remain a solid. Once it turns into sodium plus, it becomes an aqueous ion. So now that sodium has given up its electron, we have copper plus that's floating around. Well, if copper plus takes up an electron, the negative charge of the electron is going to neutralize the positive charge of the copper ion, and so the plus and the minus are going to cancel each other out, and you're going to end up with copper 0. So copper 0 is going to be your product. It's neutral copper, and that copper is going to become a metal. So essentially what we're saying here is we're trying to drive this reaction in reverse. It's very interesting. So instead of copper 2 plus, suppose you had copper 1 plus, like in the problem, and 1 electron, and that is now going to be forced to become copper. And what is driving it to become copper? Well, what's driving it is the reducing power coming from the sodium. The sodium giving up its electron makes it possible for the copper then to take that electron up and become copper 0. So the correct answer then is what we're left with is B. So sodium gives up its electron and becomes sodium plus, and the copper takes up that electron and becomes copper 0 as a solid. So now let me just bring up a very important point, and this is going to be really important also for understanding how to interpret these kinds of redox problems. Suppose I started with sodium plus, okay, and I wanted to put that electron back to get it to go from sodium plus into sodium metal. Suppose I wanted to get that from an element down here like copper. So suppose I started from copper, neutral copper, and we wanted to get the copper to make electrons, and then we wanted to use those electrons to reduce the sodium. Is there going to be a reaction? And the answer is no. There will not be a reaction. And the reason there will not be a reaction is because copper here is too weak of a reducing agent. It cannot provide sufficient reducing power to get something like sodium to accept an electron and become sodium metal. Okay, so that's a very important trend. So if you can understand that kind of a trend and how to combine two metals in a redox reaction and identify which way the reaction is going to go, or if no reaction is going to happen, or I guess I should say what your products are going to be. If you can identify your products, and if you can identify if the reaction is not going to proceed, then you understand this table very well. So I would just try to focus on those kinds of things and be like understanding how to find the products of a redox reaction between two metals and understanding what it means for no reaction to happen. So if we tried to get an electron to come off of the copper and go on to the sodium, reduce the sodium, then that reaction cannot happen because copper is not a strong enough reducing agent to get the sodium to accept an electron. Okay, so B is the right answer for number 8. The sodium metal very readily gives up its electron and reduces the copper from copper's plus to copper 0. For number 9, we have an interesting reaction here that some of you might have seen before, but this is new to a lot of us. This is a reaction that's called a complex symmetric titration. So it's a titration that's just like an acid-base neutralization, except instead of putting a base in with an acid or vice versa, what we're doing is we're trying to analyze for how much of a certain metal is in a solution by binding all of that metal up. So we do that by adding a molecule called EDTA, that's ethylene diamine tetraacetate or tetraacetic acid, sort of depends on what you're trying to do. This stuff is literally in everything. It's in our shampoos, it's in a lot of things. And so what this molecule does is it binds up metals. We can use it to figure out how much of a certain metal there is in a solution. And we do that by utilizing this equation. And we know that when we add, if we have a certain amount of zinc, and we add the same number of moles of EDTA to that solution, and we bind all of that zinc up, if we know how many moles of EDTA we add, because we can measure that, then that equals the number of moles of zinc that was present in the solution. Why? Because it's a 1-to-1 mole ratio. So really you don't have to worry about the complicated chemistry that's involved in complexing the metal and all that kind of stuff, even though I think it's very interesting. You just got to look at this equation and go, okay, well, if I add a certain amount of EDTA, I can use the equation to tell me what mole-to-mole ratio exists, or relationship exists between the amount of EDTA I added and the amount of zinc that was in the solution. So let's go ahead and utilize that relationship to figure out how much zinc was in the solution. So from my EDTA measurement, so I had some kind of a burette and I went ahead and did this experiment, I had 0.065 molar EDTA, right? And I dispensed 35 milliliters of it into my zinc solution to get it to bind all of the zinc up. This is a very analogous process to saying we added the same number of moles of base to neutralize the acid. Same exact idea, except the chemistry now is a little bit different. So here we have a volume. Let's go ahead and take this and go ahead and convert it into liters. So that now we can use the molarity equation to figure out how many moles of EDTA there was in our how many moles of EDTA we needed to dispense in order to bind up all of the zinc. That I think is a better way to put it. So molarity equals moles of EDTA per liter. So our molarity equals 0.065 molar equals moles of EDTA divided by 0.035 liters. Okay, so we have a molarity and we have the liters, so we have 2 out of the 3 things we need. Now we just want to solve for the moles of EDTA. So let me go ahead and grab my calculator and go 0.065 times 0.035. Okay, and that tells me then that the moles of EDTA is 0.002275 moles of EDTA. So this is how many moles of EDTA I needed to add in order to bind up all of the zinc. So now, consulting the chemical equation, we know that the number of moles of EDTA we put in equals the number of moles of zinc that was in our solution. And the reason we can make that assessment is because it's a 1-to-1 mole ratio. So I'll go ahead and show this. 1 mole of zinc ions are bound up by 1 mole of EDTA. Moles of EDTA cancel, and hey, look at that! Now we're in moles of zinc. Okay, now we're in moles of zinc. So once again, and I promised I'd be saying this, and sure enough I'm saying it here, the number did not change, but the units changed. Very, very important. So as long as you show your units, you can show how your conversion took you from moles of EDTA into moles of zinc. So 0.002275 moles of zinc. If you don't show your units, then how do you know what this number is? Or what it means? Yeah, you get 0.002275, but of what? I don't know. But if you put units in there, you make it very clear that these are the number of moles of zinc ion. Okay? So now that we have the number of moles of zinc ion, then all we need to do now is say, okay, from moles, 0.002275 moles of zinc, I can turn this into grams of zinc by multiplying it by the molar mass of zinc. So 65.38 grams per mole. Moles cancel, and now I'm in grams of zinc. So I'm going to just take this number and multiply it by the mass here, and I get 0.14874, and then you just round it right there, because yeah, there we go, and then so it's just 0.149. Technically, we're only allowed 2 significant figures because the molarity I provided you with had 0.65 that has 2 significant figures, but the answers here rounded it to 3, so the answer then is 0.149 grams of zinc ion. But if you had gotten 0.15 because you have actually properly rounded, then still D then would be the closest answer out of all of them to the correctly rounded number. So there we go. D is the correct answer for number 9, and that's how you'd go about doing it. So it's exactly the same thing as doing acid-base, except the chemistry is a little bit different here. Here we're doing complex symmetric titrations instead. Okay, lastly for number 10, we have a reaction of sulfuric acid and potassium hydroxide. And what we're being asked is to determine the molar concentration of sulfuric acid, that's H2SO4, in a solution if 5 milliliters of 0.1 molar potassium hydroxide is needed to completely react with 50 milliliters of the acid. So the key thing that we always have to keep in mind for doing an acid-base neutralization is that the moles of the acid have to equal the moles of the base. So if we have a certain amount of base that we added, then at the equivalence point where both of these have reacted, the acid and the base have completely reacted, we have added the same number of moles of hydroxide as there originally was protons in the solution. So if we can figure out how many moles of hydroxide we have in the solution, then we will automatically be able to figure out how many moles of protons were in there, and then from that we can figure out what the acid concentration was. So let's go ahead and do that. Let's figure out first of all what our KOH moles of KOH were. So we had 0.1 moles per liter, and we needed to dispense 0.005 liters. So what this means is that the number of moles of KOH, is 0.0005. Okay, so that's how many moles of KOH we needed in order to neutralize this acid. Now we have to play the unit dance to get us from KOH into H2SO4. So we know that from the neutralization that 0.0005 moles of KOH is what it takes to neutralize this solution. So the chemical equation here allows us to convert into H2SO4 by a mole-to-mole ratio. Now, this mole-to-mole ratio is no longer 1-to-1. So I was also foreshadowing this in the previous video, if you had a chance to see it. And that is that when everything is 1-to-1, you're just playing around with units. You're not changing any numbers. Here, both units and numbers change. It's very, very important. So here, if we want to convert into moles of H2SO4, we have 1 mole of H2SO4 that reacts with 2 moles of potassium hydroxide. Now our moles of KOH cancel, and we are left in moles of H2SO4. So now that we have moles of H2SO4, let me go ahead and write that out. So 0.00025 moles of H2SO4. Now that we have the number of moles of H2SO4, we can use the molarity equation, because all these answers are in molarity. We can use the molarity equation to tell us what the concentration was. So molarity equals moles of H2SO4 per liter. We know 2 of these things. We know how many moles of H2SO4 we have. That's this. And we know how many liters of H2SO4 we have. That's given in the problem as 50 milliliters, or 0.05 liters. And so then we can solve for the molarity. So let's go ahead and do that. Moles of H2SO4 is 0.00025. Not very many moles, that's for sure. Divide that by the volume, which is 0.050 liters. Moles per liter give us molarity. So now I can just go ahead and go 0.00025 divided by 0.05. And what that gives me is a molarity of a 0.005. So that's 0.005 molar H2SO4. So that corresponds to D, so D is the correct answer for number 10.